So, the last time we looked at iterated hill climbing, in which the approach that we took was that we choose random starting points and uh, do hill climbing from all of those points. And the idea was that for solution space search, the starting point is of no consequence. You could start from anywhere. It is the goal that you are interested in. Now, we will look at a few algorithms where the actions themselves are stochastic, which means that you are considering an action and you want to decide whether to take that action or whether to make that move or not to make that move. Okay. So, let us look at a few algorithms which do this. The idea is again that you would like to consider actions which are good, which improve the evaluation function or the heuristic function, but sometimes you want to even make moves which are not necessarily good, and the objective is still the same, that you want to move away from local maxima if you get stuck there. So, hill climbing, we have said, does exploitation of the heuristic function, and it basically follows the gradient essentially. The opposite of that is, some sense, is a random walk, and what the random walk does is that it just chooses a random move and makes that move essentially. So, you just choose one random move and you make that move. So, in that sense, the search kind of wanders through the space, whether it is the state space or the solution space, and the only thing we do is that we keep track of the best, that wherever we find a good candidate, we keep track of that, and eventually we want to return the best essentially. So, this is as opposed to hill climbing, which does pure exploitation. Random walk does pure exploration, and we want to look at algorithms which do a combination of the two. The first algorithm we are interested in is called stochastic hill climbing. So, it is like hill climbing, except that you do not necessarily move to the best neighbor. In fact, you adopt the approach that we took for random walk, is you generate a random neighbor. So, you are at a given node V C. So, C stands for current and V stands for vertex, and then you select a random neighbor V n and compute the difference in the evaluation functions essentially. So, we traditionally call this difference as delta E, and we will see shortly that this is because it has some connotation with energy essentially. So, the difference is the eval V of n minus eval V of C. Now, you observe that if delta E is positive, it means that V n is better than V C, and the algorithm should move to it with a high probability. That is the idea of stochastic hill climbing. But if delta E is negative, it means that V n is worse than V C, but the algorithm should still move to it, but with a lower probability. So, the algorithm has a higher probability of making good moves and a lower probability of making bad moves, but it can do moves in both directions. So, in that sense, it has this flavor of random walk, where it can move to either a better move or better node or a worse node, but the probabilities are different. How are these probabilities computed? We use what is called the sigmoid function. So, the question, as you can see, is that you are at V C and you have generated V n, and you want to ask whether to move to that V n or not to move that to that V n. So, that is what we said, accept a good random move with high probability, accept a bad random move too, but with a low probability. This will combine both exploration and exploitation. Because you are accepting good moves more often, you are also doing exploitation, but because you are doing accepting bad moves, you are also doing exploration. So, the probability of making that move is given by this function, where we have already seen that delta E is the difference between the two valuations, and this function is called the sigmoid function, and it is given by 1 over 1 plus e raised to minus delta E by t, where t is some parameter that we will eventually control. For the moment, we will assume that it is fixed essentially. So, delta E, as you know, is the difference between the evaluation functions, and t is a parameter. How does this function look? This basically this function looks, this is the shape of a typical sigmoid function, that at when delta E is equal to 0, the probability is 0.5, and as delta E increases, the probability becomes more than 0.5 and tends to 1 eventually for very large delta E, and when delta E is less than 0, the probability, as you can see on the left hand side, is less than 0.5 essentially. So, that is a lower probability. So, let us look at a physical process called annealing.
So if the delta is 0, right? So that means the VC and VN are at same level, right?
Yeah, at the same
So
level.
it
That
must
means
be
that
a
it could be
plateau
a
kind of a
plateau. It
thing.
could be a
Yeah.
plateau kind of a
So
thing.
there is no need to move, right? That means, or did I get it wrong?
Well, we want to do exploration. That's why we are moving even when they are equal, but we are moving with a probability of 0.5 essentially. See, this need to move would be meaningful if you were doing something like hill climbing. Then you'll say, okay, only if the node is better you move, but that would be pure exploitation. We want to introduce this element of exploration, which means that you want to keep searching the space as much as possible essentially. And this is just a uniform way of doing this essentially. So, let us look at this physical process of annealing. So, in metallurgy and material science, annealing is a heat treatment process that alters the physical and sometimes the chemical properties of a material to increase its ductility and reduce its hardness, making it more workable. So, it is a very commonly used practice in material science. It involves heating a material above the recrystallization temperature, maintaining a suitable temperature for a while, and then cooling it down in a controlled fashion. So, that is controlled by something called a cooling rate essentially. In annealing, the atoms migrate in the crystal lattice and the number of dislocations decrease essentially. So, what really happens is that the material settles down into a low energy state. That is where the term delta E comes from, in the sense that we are trying to minimize the energy state of the material, and we are doing it by raising it to a temperature and then cooling it down. So, that is where the parameter T also comes from. T stands for the temperature. So, essentially this process by heating up and then carefully cooling so that the atoms settle into that crystal structure is called annealing, and it's a bit of an art that is used in with materials. So, we are looking at an algorithm called simulated annealing, which will begin with exploration and end with exploitation. So, if you remember the sigmoid function, its probability depends on two things, one is delta E and one is T essentially, and now we will vary T, but of course delta E we will get from the domain essentially. So, the algorithm is just a variation of stochastic hill climbing. You start with a random node and you always keep track of the best node essentially. Then choose T as some large value. We will see in a moment that large T means the probability is equal for good moves and bad moves essentially. So, we start with a large T, which means that we are encouraging exploration, and we do the following for some number of epochs essentially. So, within this epoch we keep T as constant, and then under for some number of termination criteria we do a sequence of iterations. This criteria could typically be, for example, some m cycles or something like that. What do? We do what stochastic hill climbing does, which is you choose a random node neighbor, compute delta E, and then decide to move to that node with a probability which is given by the sigmoid function. So, this is a sigmoid function if you remember, and what we do is that we generate a random number between 0 and 1, and so if this is the range of the random numbers, this is 0 and this is 1, and this value is somewhere here in this range. So, if we now generate a random number, if it comes in this range, then we make a move. If it comes in this range, we do not make a move. So, in this manner, we have made a move probabilistically, and the probability is determined by delta E and t, and that is a function that we saw earlier, right, and we will see it again in a moment. So, if the random number is in the range which is less than the probability, then we make that move. That means, we neighbor becomes a new node, and of course, we keep track of the best at all points of time. Then we get out of this cycle at some point after these, let us say m cycles, then we reduce the temperature. So, this is a simulated part of annealing essentially, that in annealing what did we do? We raised the material to a high temperature and gradually brought down the temperature, so that the atoms settle down into a nice crystalline structure. We are trying to do something similar here, is that after the first cycle, we reduce the temperature a little bit and then do the whole thing again. Then again reduce the temperature a little bit and do the whole thing again. So, this cooling function basically is a lowers the temperature after each cycle essentially, and the function random number generator between 0 and 1 generates a number which tells us whether to accept that random neighbor or not essentially. So, that is the idea of simulated annealing. You start at a high temperature and gradually cool down the temperature, and what happens is that initially the moves are more random, and gradually as temperature lowers down, they become more and more deterministic, more and more controlled by the gradient essentially.
So, we can, the delta E is the probability, right? Using delta E,
Delta
we can
E is
find
the
the probability.
difference between the evaluation values. Delta E is the evaluation value of the neighbor minus the evaluation value of the current node. So, what we call as Vn and Vc essentially. N is a new neighbor, C is the current node. The difference in their evaluation functions is the delta E, and if it is positive, that means for a maximization problem, we are going to a better node essentially. And so, this whole formulation is for a maximization problem, and if it is a better node, we want to move with a higher probability. That is what the sigmoid function tells us essentially. So, if you remember, the sigmoid function is essentially like this, and at some point where delta E is equal to 0, the probability is 0.5. We will see this again, but if delta E becomes positive, then the probability becomes more than 0.5, which is in this region. If delta E is negative, then the probability is less than 0.5, which is in this region essentially.
And that probability, let that be below 0.5 or above 0.5, is judged by this random thing, right? So, there is a function called random.
That is only a mechanism to make that move probabilistically. So, supposing this value was 0.7, okay, that you want to make that move with a probability 0.7. How do you implement that? So, one simple way to implement is to generate this random number from 0 to 1. If that random number is less than 0.7, that means it will fall in the range which is here, somewhere in this range. Then anywhere in this range you accept that move. If it is more than 0.7, then anywhere in that range you accept. So, you take an example, another example. So, for example, if the probability was 0.9, okay, that means you want to make the move with a high probability, then the range in which the random number is allowed to fall is high essentially. On the other hand, if the probability was to be 0.2, then this range would be very small. You would make the move only if the number you generate is in that range essentially. So, this is just a mechanism for making the move probabilistically. The probability is determined by the sigmoid function, and that is determined by delta E and t essentially. And t, as we have said, we are going to be decreasing gradually.
Right. So, if we consider that there are 2 points, 2 nodes, and one has the probability of 0.9, one has 0.2.
No, see, you are only generating one neighbor, and you are trying to decide whether to move to that neighbor or not. So, you compute the probability and then based on that you either move to it or you do not move to it, I think. So, you are only considering one neighbor at a time. So, in that sense this is different from hill climbing. In hill climbing what did we do? We generated all the neighbors and picked the best one. We did the same in taboo search as well. Here we are not doing it, we are following the technique of random walk, which means you generate a random neighbor and either move to it or you not move to it based on this probability, I think. So, if you remember that when we looked at variable neighborhood descent, one of the reasons we considered that doing that was that as you increase the density of the neighborhood function, we saw various neighborhood functions. The computation needed to make one hill climbing move was higher for denser functions. So, that is why we said we will start with sparse functions and then move on to dense functions, but there we were computing all the neighbors. Here the difference is we are not computing all the neighbors, we are just generating one random neighbor and deciding whether to move to that or not. So, how is the probability influenced by the two factors? There are two factors, one is delta E and one is T essentially. So, let us look at the effect of T on probability. We already know that the probability of making a move increases as delta E increases essentially. So, on beyond delta E equal to 0, the move probability which should be greater than half at least. So, for very large t tending to infinity if you want to speak mathematically, but for very large t, the algorithm behaves like a random walk, and this is if you just plug in a large value of t into the sigmoid function, you will see that probability will be 0.5 irrespective of what delta E is essentially. As for t equal to 0, the behavior becomes like deterministic, like hill climbing, which means that if delta E is greater than 0, the probability of making that move is 1, and if delta E is less than 0, the probability of making that move is 0. So, this part is as you can see less than 0 and this part is a greater than 0, and the probability is deterministic essentially. In between, as we cool the temperature, remember that this algorithm says that you are going to lower the temperature, starting with a random walk which is for very large t, it gradually moves towards hill climbing. So, this is like hill climbing, that accept a move only if it is good and do it deterministically. So, the probability is 1 essentially, that is what I mean by saying deterministically. As we reduce the temperature, the search becomes more and more exploitative and the shape of the sigmoid function changes. So, initially it was horizontal, now gradually it is opening up, essentially it is going down in the left hand side and going up in the right hand side, and this is happening as temperature is reducing essentially. As temperature goes lower and lower, it tends to become more and more like hill climbing essentially. And it has been observed that in practice simulated annealing is a very good optimization method. So, let us see the effect of temperature in this table, which I have taken from this book called How to Solve It, Modern Heuristics. It is quite a nice book, and here we are fixing delta E at 13, which means it is a better node, V of n is better than V of this thing. Minus delta E is the negation of that, which is minus 13 essentially, because in the formula we are using minus delta E by t, right. So, this we are fixing delta E to 13. So, we are computing what we see in the second column is the value of e raised to minus 13 divided by t as t varies. So, you can see that as on the top when t is equal to 1, which is a very low value, that value is very small, and because that is in the denominator of the sigmoid function 1 plus e raised to minus 13 by delta t, the sigmoid function tends to become equal to 1 essentially. So, when temperature is very low, the probability is close to 1 essentially. That is what we saw in the figures when we looked at different values of sigmoid function. When t is very high, then this component e raised to minus delta e raised to minus 13 divided by delta t tends to 1 essentially. So, e raised to 0 would be like close to 1 or at least of the order of 1, and then the probability is 0.5. Temperature, remember in our these things we are reducing temperature. So, we are going to be moving in this direction. We are going to be starting with a high temperature and going towards a lower temperature. And for the same delta E, as you can see, as we go from high temperature to lower temperature, the probability of making that move increases essentially. And remember that when we say delta E equal to 13, we are saying it is a better move essentially. Let us look at the effect of delta E itself. Let us keep the temperature fixed. So, here we have fixed the temperature at T equal to 10, and the starting node is 107, has a value of 107, and these are the different possible values of the neighbor node essentially. So, we have varied it from 80 to 100 to 107 to 120 and 150. So, 107 of course is equal to V of C. So, which is why this delta E is 0, and when delta E is 0 and we have fixed the temperature to 10, you can see that the probability is 0.5 essentially. So, if the node is same as this one, you move to it or you do not move to it, it is a bit like random walk essentially. But as the value of the neighbor increases, which means it becomes a better node, then delta E, I should write minus delta E. So, minus delta E becomes minus 13 as we saw in the previous table, or and then it becomes minus 43. As delta E increases or negation of delta E decreases, you can see that the probability is tending to 1 essentially. The better the neighbor, the greater the probability of moving to that. For nodes which are worse than VC, remember VC is 107. So, 80 and 100 are less than 107, these are worse than that. You can see that the probability is much lower than 0.5 essentially. So, you would make a bad move, but with lower probability, and you would make good moves with higher probability. So, in that sense it would have a tendency of moving from poor nodes to good nodes. So, this is an example which this is a intuition which I try to work with. It says that let us say you are at two different local maxima, your basic task was to escape from one maxima and go to a better maxima. So, if you are at two local maxima, one is on the left which is A and the other is here which is B. How do you go to that? You would have to traverse down. If you want to go from one to the other, you would have to traverse down against the heuristic function or against the evaluation function or against the gradient, and then climb up again. So, this climbing up part will happen naturally because the gradient pulls it up essentially. It is the going down part which is going to be a less probable event essentially, because we have said that make bad moves with lower probability. Now, because this delta EA, so going down to let us say this middle point M, from if you want to go from A to M, then the amount of delta E that you want to overcome is shown by this arrow on the left. On the other hand, if you want to go from B to M, then the amount that you have to overcome is much larger than that. So, you can see that the probability of moving from A to M is going to be much higher than the probability of moving from B to M essentially. And this is what we want essentially, that if you are at a local maxima in this case, you should be able to move off that and then go off to the next maxima and so on, and this is what simulated annealing does in practice essentially. So, this is just an intuition of how you can understand how these moves are being affected by delta E and T. Delta E is this as shown in this diagram here. T is of course saying that the probability of, as t comes down, the probability of making bad moves also comes down. So, in some sense, if you are stuck in a nice place, then with low t you will just go to that local maxima from their point, and hopefully that local maxima will be close to the global maxima. There is no guarantee of course that you will find the global maxima, but simulated annealing in practice has worked very well essentially.
Sir, when we say that we are using the cooling function, we are decreasing the t values, right?
We are decreasing the
So
t value.
that means it is easier to move when the t value is.
When the t value is low, uh, good moves are made and bad moves are not made in some sense. Of course, there is a probability involved that depends on the temperature, but at very low temperature only good moves will be made and bad moves will not be made, because as we saw in the probabilities, if you look at this table on the top right, at very high t the probability is 0.5, at very low t the probability is close to 1, but this is because the neighbor is better than the current. If you were to draw a corresponding table for one of these other values, let us say V of n is equal to 80 or 100, you will see that at very high temperature the probability will remain 0.5, but at very low temperatures the probability will tend to 0 essentially, if you choose a worse node essentially. So, the effect of temperature is that initially it is behaves like a random move, but as temperature comes down it becomes more and more like hill climbing essentially. So, in a situation like this, if the heuristic function or the evaluation function were to be something like this, then in general simulated annealing works well. What I have shown with these two vertical bars is that the footprint of hill climbing is very small, that only if your starting point is in one of these locations will hill climbing succeed, otherwise hill climbing will get stuck into one of the many local maxima that you can see here essentially. But simulated annealing is manages to overcome those local maxima. So, if it is here for example, it manages to go here and then it manages to go here and then it manages to go here and so on, and it has been seen in practice that it works quite well.
Sir, sorry.
Yeah.
Yeah, one question. When the probability increases, it's from the previous slide. So when the probability increases, how is that correlated with making good moves? It only makes that it only makes sense that we are moving, right? When probability is more. What does it say about making good moves?
So, that is what you can see on the table on the right hand side. So, the middle row where V of n is 107, which is equal to V of c is 0, delta E is 0, right. And you can see that we have chosen some temperature T essentially, the probability is 0.5. Now, below the middle row, the two other values that we are looking at of V of n is 120 and 150 for the same temperature, which is T equal to 10. What is the probability? The probability of moving from 107, 107 remember is V of c and the neighbor is V of n. So, probability of moving from 107 to 120 is 0.78 as you can see here. The probability of moving from 107 to 150 where delta E is 43 is much higher, which is 0.1. So, the better the move, the higher the probability. At the same time, the probability of moving to a worse node, which is for example 80 or 100, is respectively 0.06 and 0.33, which is a lower probability.
But in this case, we kept the t value as constant, right?
So, this is just to understand the effect of delta E and delta T. We have these two separate tables. Yeah. In practice, what happens? You start with some very large value of T, and then you go through this cycle of making this some m number of random moves essentially. Then you reduce T, then again you go through this cycle of making some m number of random moves, and you keep doing that.
Okay, so in this cycle, the node that makes the good move will eventually get selected, right? So that's the
So,
idea.
initially all neighbors would get selected because temperature is very high, and we have seen in the table that when temperature is very high, so even from this you can see that when temperature is very high, the probability is 0.5. So, whether it is a good neighbor or a bad neighbor, you would make that move. But as temperature decreases, so for example, at some point this is a curve that is uh, determining your behavior essentially. So, at that point you can see that for a positive delta E, the probability is higher than 0.5, but for a negative delta E, the probability is lower than 0.5. And as temperature is reduced, that is what simulated annealing is doing, that you gradually reduce the temperature. You keep it at very high value, you do m number of random moves, then you bring it down, then you do another m random moves, and you keep doing that essentially, and eventually T will come down low, at which point only good moves would be accepted. As you can see, for example, for this curve here, the probability of selecting even a slightly better move is quite high, uh, and this probability of so if this is the curve that we are looking at, of making even a slightly uh, worse move, which means this is the delta E that we are talking about, can be quite low essentially. So, it becomes more and more like gradient ascent as temperature comes down essentially. Okay. So, next we will look at population based methods, which is also inspired by something which happens in nature, which is the evolution that happens in the real world or survival of the fittest. So, we will do that in the next